Try to unscramble an egg, take a whisk, stir the mess backward, and somehow reconstruct a perfect intact yolk sitting inside its shell. Obviously impossible. Now imagine you'd never once seen a raw egg, only ever the scrambled version, and someone asked you to work out, purely from that yellow mush, exactly what it used to look like before anyone touched it. That's roughly the position cosmologists find themselves in every single day. We live inside a universe that has been thoroughly stirred, stretched, and cooked for nearly 14 billion years, and our job is to somehow work backward from the scramble to the egg. Thanks to instruments like the James Webb Space Telescope, we can actually watch parts of that cooking process happening in reverse, captured in ancient light that left its source billions of years before Earth even existed. But the deeper we look, the stranger the picture becomes, and in the last few years, that picture has started throwing up genuine contradictions, findings that simply don't fit the models scientists have relied on for decades. When the James Webb Space Telescope released its first science images in July 2022, the excitement in the astronomical community was immediate. This is a 6.5-ton spacecraft carrying a sun shield roughly the size of a tennis court and a primary mirror with 6 times the light collecting area of Hubble's, tuned specifically to infrared wavelengths, the exact part of the spectrum needed to catch extremely faint, extremely ancient starlight that has been stretched by cosmic expansion on its way to us. Because light takes time to travel, looking farther away is functionally the same as looking further back in time. And Webb was built specifically to look as far back as physically possible, toward the very first stars and galaxies that ever existed. One of the earliest, most striking results was an image known as Webb's first deep field, a patch of sky so small that a single grain of sand held at arm's length would completely block it from view. Almost nothing in that image is an individual star. Nearly everything you see is an entire galaxy, some so distant their light has been gravitationally bent and smeared by the mass of closer galaxies sitting in front of them. Buried in that image is one of the oldest galaxies humanity has ever detected, its light having traveled roughly 13.1 billion years to finally reach us, meaning we're seeing it exactly as it appeared at the very dawn of the universe's existence. To understand why findings like this matter, you first need to understand how scientists arrived at the widely quoted figure that the universe is 13.8 billion years old in the first place, because the reasoning behind that number is more approachable than most people assume. It starts with a simple observation made in the 1920s. The universe is expanding, with essentially everything moving away from everything else, at a rate astronomers call the Hubble constant. Belgian cosmologist Georges Lemaitre realized that if the universe is expanding and cooling now, running the clock backward means it must have once been smaller and dramatically hotter, with all of its energy compressed into an increasingly tiny volume. Wind that process all the way back, and you arrive at a single, infinitely dense, infinitely hot point that then explosively expanded outward, eventually cooling and spreading into everything we see today. This is the basic premise behind what's called the hot Big Bang model. Pinning down exactly when that expansion began requires a handful of foundational assumptions. That the universe is roughly uniform in density on the largest possible scales, despite the obvious clumping of galaxies into clusters and voids on smaller scales, that the same physical laws apply everywhere, in every direction, and that the Big Bang itself didn't happen at some specific point in space that we could point a telescope toward, but rather happened everywhere simultaneously, since the expansion of the universe is really an expansion of space itself, not an explosion moving through pre-existing space. Because the current expansion rate implies that sufficiently distant galaxies are receding from us faster than light itself, there exists a boundary beyond which no light emitted today could ever reach us. Everything within that boundary makes up what astronomers call the observable universe, and it's genuinely all we have any ability to study directly. With those assumptions in place, astronomers can use multiple independent methods to work out the universe's age. One relies on white dwarf supernovae, which reliably explode with almost identical intrinsic brightness, meaning any given supernova's apparent dimness directly tells you how far away, and therefore how far back in time, you're actually looking. Another relies on the cosmic microwave background radiation, essentially a fossil imprint of the universe as it existed just 380,000 years after the Big Bang, when the entire cosmos was roughly 2,000 degrees Celsius, hot enough to emit visible light at the time, though the expansion of space since then has stretched those original wavelengths by a factor of roughly 1,000, shifting them into the microwave range we detect today. This makes the cosmic microwave background quite literally the oldest light humanity has ever observed, and because there are almost no other significant sources of microwave radiation cluttering the sky, it offers a remarkably clean snapshot of the infant universe, showing the faint density fluctuations that would eventually seed every galaxy, cluster, and filament we see today. Combining these independent methods, alongside our understanding that the universe consists of roughly 68% dark energy, 27% dark matter, and only about 5% ordinary observable matter, three completely different measurement techniques converge on essentially the same answer: 13.8 billion years, with roughly 99% confidence. For a long time, that agreement across independent methods felt like a genuinely satisfying confirmation that our model of the universe's origin was fundamentally correct. But cracks have started appearing, and one of the first came from something as ordinary as measuring the ages of individual stars. Certain very long-lived stars, ones that formed from primordial matter shortly after the Big Bang, should still exist today, essentially unchanged, offering a kind of fossil record of the earliest epochs of star formation. That's exactly what makes a star called Methuselah so significant. It's an extremely metal-poor, and therefore extremely old, star located only about 200 light-years from Earth, close enough to study in genuinely fine detail. Based on careful analysis of its evolutionary state, astronomers estimate its age at roughly 14.5 billion years, with an uncertainty of plus or minus around 800 million years. A figure that, taken at face value, would make Methuselah older than the universe itself. The James Webb Space Telescope has added its own layer of tension. In early 2025, Webb detected its most distant confirmed galaxy yet, cataloged as MOEM Z14, dated to roughly 280 million years after the Big Bang. The timing doesn't technically contradict the 13.8 billion year figure, but it does raise a genuine problem. Models of galaxy formation didn't expect galaxies this bright and this large to exist that early. Building a galaxy takes time. Interstellar gas and dust need time to gravitationally collapse into stars. Those stars need time to live and die, and their remnants need time to seed subsequent generations of star formation. Finding a fully formed, brightly shining galaxy at such an early cosmic moment suggested either our timeline was somehow wrong, or the process of galaxy formation happens far faster than anyone had modeled. And it wasn't an isolated anomaly. As Webb's data accumulated, the early universe it revealed wasn't the sparse, barely forming proto-universe cosmologists expected. It was crowded. Galaxies appeared too numerous, too bright, and the supermassive black holes sitting at many of their centers appeared to have grown far too large, far too quickly, to match existing formation timelines. Some of these tensions turned out to have relatively straightforward explanations. The unexpected brightness of many early galaxies, which initially implied an impossibly large population of stars for their age, was partly resolved by researchers at the University of Texas studying Webb's early survey data, who realized much of that excess light likely wasn't coming from stars at all, but from actively feeding black holes at each galaxy's center, their accretion disks glowing intensely from friction as gas spirals inward. Once that extra light source was properly accounted for, the implied stellar mass of these galaxies dropped back into line with existing models, resolving one piece of the puzzle. But in doing so, it simply relocated the mystery. If black holes were responsible for that excess brightness, how did black holes that massive form so early in cosmic history in the first place? Small, stellar mass black holes, formed from the collapse of massive dying stars and typically weighing anywhere from a few to roughly 100 times our sun's mass, aren't a problem. There was plenty of time for stars to live, die, and collapse into these in the early universe. The genuine puzzle involves supermassive black holes, weighing anywhere from tens of thousands to billions of solar masses, typically found anchoring the centers of galaxies. Growing a black hole requires feeding it a steady supply of infalling matter, and that process has a hard physical speed limit, described back in 1920 by British astrophysicist Arthur Eddington. Because photons carry momentum, even a small amount, infalling matter has to push against a constant outward pressure of escaping light as a star or accretion disk grows brighter. Past a certain brightness threshold, that outward radiation pressure overwhelms gravity entirely, blowing away any further infalling material. This ceiling, known as the Eddington limit, explains why extremely massive, extremely bright stars, like Wolf-Rayet stars, more than 20 times the sun's mass, sit right at the edge of blowing themselves apart. And it applies just as forcefully to the luminous accretion disks surrounding growing black holes. Run the numbers, and growing a modest stellar mass black hole into a genuine supermassive black hole within the time available in the early universe would require feeding continuously, right at the Eddington limit, without interruption, from the moment of formation, something real black holes essentially never do, since they routinely run short of nearby material and have to wait for more to arrive. Compounding the problem, astronomers have struggled to find convincing evidence of intermediate mass black holes, the theoretical middle step between small stellar remnants and full supermassive giants. If stellar black holes gradually grow into supermassive ones, that intermediate population should be relatively common. Instead, it's suspiciously, almost completely absent from our observations, with only a small handful of uncertain candidates ever identified. This gap has pushed some cosmologists toward an entirely different hypothesis, that in the far denser conditions of the early universe, Massive clouds of gas and dust might have been able to collapse directly into a black hole, skipping the intermediate stellar stage altogether, potentially explaining how some supermassive black holes could have effectively been born large from the very beginning, a process that may simply no longer be physically possible in today's far more diffuse universe. Then a specific object seemed to tip the argument back the other way entirely. A black hole catalogued as LID 568, located somewhere between roughly 12.1 and 12.3 billion light-years away. So distant and so heavily redshifted into infrared wavelengths that it took the combined resolving power of the Chandra X-ray Observatory's Cosmos Legacy Survey and the James Webb Space Telescope working together just to detect it at all, appearing even then as little more than a faint, compact red smudge. Yet the X-ray emission from its accretion disk told a remarkable story. LID 568 appeared to be consuming matter at roughly 40 times the Eddington limit, a rate that shouldn't be sustainable at all under standard physics. It turns out exceeding the Eddington limit isn't entirely impossible, just extremely difficult to sustain. If a black hole's outward radiation is concentrated into narrow, focused jets rather than escaping evenly in every direction, matter can continue falling and relatively unimpeded from other angles. There's also a brief window before radiation pressure fully overwhelms gravity, where an unusually greedy black hole can grab hold of escaping matter and briefly exceed the theoretical limit before eventually paying the price later. If LID 568 really was accreting matter at such an extreme rate, it would offer direct observational proof that supermassive black holes could plausibly reach enormous sizes far faster than standard models allowed. But subsequent scrutiny complicated that conclusion. In a paper published in the Astrophysical Journal, researchers Dongyao Kim and Youngjin Kim revisited the original Webb data and determined that dust surrounding LID 568 had likely been obscuring the black hole considerably more than earlier estimates accounted for. Because you need to know a black hole's true brightness to accurately calculate how much mass it's consuming, correcting for that additional dust dramatically changed the numbers. Once the new values were applied, LID 568's accretion rate dropped back to something far closer to ordinary Eddington-compliant levels, essentially removing it as clean proof that black holes can casually blow past their theoretical growth limit. The mystery of how supermassive black holes formed so quickly in the early universe remains for now genuinely unresolved. There's one more thread in this larger tension, involving an element most people encounter every single day without a second thought: lithium, the metal sitting quietly inside your phone's battery. Lithium is soft enough to cut with an ordinary kitchen knife and reacts vigorously with water. But what makes it relevant to cosmology is its remarkably simple atomic structure, just 3 protons, making it one of only a few elements light enough to have plausibly formed within the first few minutes of the universe's entire existence. Working through the physics of those earliest moments, roughly 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Celsius, still far too hot for atomic nuclei to form, existing instead purely as radiation, the same radiation that eventually became the cosmic microwave background. Roughly 99 seconds later, the universe had cooled enough to about 1 billion degrees for the strong nuclear force to bind protons and neutrons together, forming the first hydrogen nuclei, and shortly after, helium through nuclear fusion. Run the equations forward, and the primordial universe should have ended up almost exactly 76% hydrogen and 24% helium by mass, with an extraordinarily tiny fraction, roughly 7 parts in 10 trillion, fusing further into lithium. Measuring the actual composition of ancient, unevolved stars through spectroscopy, examining precisely which wavelengths of light get absorbed by specific elements as starlight passes through surrounding gas, largely confirms these predictions for hydrogen and helium remarkably well. Our own sun, having undergone billions of years of additional fusion, sits at roughly 71% hydrogen and 27% helium, consistent with a star that formed later and altered those original ratios somewhat through its own nuclear activity. But lithium refuses to cooperate. The observed abundance of lithium in ancient stars comes out to roughly 1/3 of what Big Bang nucleosynthesis predicts it should be, a persistent, well-documented shortfall astronomers call the lithium problem. Making matters stranger, the specific ratio between lithium's 2 main isotopes, lithium-7 and the rarer, supposedly far less common lithium-6, is also wildly off from predictions, with lithium-6 showing up roughly 1,000 times more frequently in ancient stars than standard models expect. So does this mean the entire hot Big Bang framework needs to be scrapped? Not necessarily, and most cosmologists remain cautious about drawing that conclusion. The model still explains the existence and detailed structure of the cosmic microwave background, and the predicted abundances of hydrogen and helium remarkably well, arguably too well to dismiss as coincidence. Even Stephen Hawking, who had been among the most prominent early advocates for the idea that the universe began from a singular point, later grew more skeptical of that specific detail, writing that once quantum effects are properly accounted for, the initial singularity itself may not need to have existed at all, even while the broader framework of an expanding, cooling universe remains intact. Resolving the lithium problem specifically may come down to one of two possibilities. Either our theoretical predictions need refining, or our observations themselves are systematically off. There's real reason to suspect the latter. Measuring trace elements in stars this ancient and this distant is extraordinarily difficult, and something happening inside these primordial stars themselves, some internal process not yet fully understood, could plausibly be quietly destroying lithium, or altering the ratio between its isotopes, in ways our current models simply don't account for. If observational techniques improve, or if astronomers identify whatever stellar process is skewing these measurements, the lithium numbers may eventually settle back into agreement with the standard model on their own, without requiring any fundamental rewrite of Big Bang cosmology at all. What ties Methuselah's uncomfortably old age, Webb's unexpectedly crowded and bright early universe, the puzzle of supermassive black holes forming faster than physics comfortably allows, and the stubborn shortfall of primordial lithium together isn't necessarily a single grand flaw in our understanding of cosmic origins. It's a reminder that every one of these threads, however small, has to eventually reconcile with every other thread before we can claim to have genuinely reconstructed the earliest moments of everything that exists. Some tensions, like the early galaxy brightness problem, resolve themselves once scientists found the right missing piece. Others, like lithium, have persisted for decades without a clean resolution. Whether the eventual answer requires refining our observations, adjusting the fine details of Big Bang cosmology, or something nobody has proposed yet, remains genuinely open. What's certain is that piecing together exactly how the universe went from an infinitely dense point to the sprawling, galaxy-filled cosmos we inhabit today remains one of the most active, most contested, and most genuinely unfinished stories in all of science. An egg that, more than a century after Lemaitre first proposed how it got scrambled in the first place, we're still very much in the process of trying to put back together.